let's begin, shall we? Always wait. The pause. There it is. It's coming. Start the stream. I think it says online. What do you know? Okay.
Those are Common Core math standards, Ben.
Yes, they are.
Yeah.
No, actually, those are Kansas College and Career Ready standards.
Oh yeah, totally.
Because the
different,
Common
sure.
Core
Yeah.
is like, you know, centralized government is really bad when it comes to it. Never mind, I shouldn't say that loud. Good morning. How's everybody doing? Semester is, this is the part where it's dragging, I'm guessing, right? So, let's see here, where to begin? I was going to start a little bit with, we left off and I didn't get a chance to do much on top about homework. Homework 2 is due, what is it, next Friday, a week from today. Part of it's pretty self-explanatory, like part 1, find an article, be a reviewer. Okay. Anybody, I've talked to a couple of you found articles. Anyone has problems with that, let me know. We can try to make that work. What I'm trying to get you to do by doing or being a reviewer is to realize kind of the big picture, at least in my mind, and I'm heavily influenced by thoughts of some of my colleagues, that peer review is always in the eye of the reader, even after the article has been published, right? So even if, a lot of times I've heard people say, oh, look, it's published. Like, it's now written in stone somewhere. You know how science works, though. A lot of things that are published now, you know, may look good at the time they're published, only to be found out wrong. Alternatively, the cynic in me thinks the peer review process is terribly flawed. I'm an outgoing co-editor of a journal right now, and I can tell you I'm part of the problem right now. But I don't know, Dr. Hoffman, would you have anything to add on that?
Yeah, published just means 3 people were convinced that you knew what you were doing.
Or less, actually.
Actually 2.
Yeah, depending on where you send it. Yeah, so just have that in mind. That, you know, there's sort of, it's tough when you're especially when you start reading this. When you start to learn how to review, how many of you have done reviews before for papers? Not a whole lot, right? It's a skill to learn, and it's really hard because you don't ever know. I remember when I started, I would spend like all day. I would read a paper, I'd write this book report that was like 4 or 5 pages. And now on the other side of the fence, yeah, there are people who do that, but generally speaking, the average review is, you know, like I said, 500 words, 300 to 500 words. It's tiny, right? So when you think about that, now you get 2 people on average submitting 500 words about a journal article. You see the same, both of you are associate editor. Do you see the same thing with your reviewers?
Yep.
So it's an interesting world. It's all volunteer, it's all hard to do, and there's lots of problems with it. I'd love to find a fix for it, but so part of what I'm trying to do with it is get you to think about that not every published article is awesome, right? Some are certainly, but you know, we all do the best we can. We all get it published, but there's always things to critique about articles. Second, the other part is that, hey, try to be a reviewer, try to have a critical lens. How do you look at articles go forward? And the third is how do people write about their Bayesian analyses? And starting with linear models, because again, it's still the place where we're at. The good news about linear models, by the way, is that today is the last linear models part. And pretty soon we're going to do linear models with latent variables. We call those measurement models. So that's like next week. Next, the Bayesian data analysis and write-up. I really glossed over this quickly last week. Does anyone want to talk about this or think about it? Anyone tried it? It's cool if you have. Maybe you have, maybe you haven't. I like this story. You want to hear the story behind the story? We have the person who I think generated it.
It's the golf one.
Yeah, the miniature golf.
Yeah.
Although this time I changed it to Midwestern Rectangular State University.
Oh, my homeworks always take place at Midwestern Red State University.
That's because you've always worked there, but this is not necessarily as red of a state where you've worked. So, but they're all rectangles. That's how I like to call them. The Midwestern Rectangular State. Basically, the idea was on this. We put people and randomly assigned them to different types of training groups. Whether or not they had, let's see here, they had a control group where they got no training, a group where they had miniature golf training only. Does anybody know what miniature golf is? You putt, yeah. Does anyone to do that here in Iowa City or the area?
On a regular golf courses.
Oh yeah, but you gotta like have like clubs and money and stuff.
Yeah.
Well, you can do miniature golf there, it just takes way longer.
Oh yeah. I'll bet you could drive a cart maybe, right? Yeah. The greens are all flat though. You gotta have those opening drawbridges and like anyway.
Like a pirate mouth.
Yeah, that's exactly it, right? Water hazards that are on the green. Anyway, miniature golf only, regular golf only, and then a blend of the two. This is a very shortened form of the assignment. In the class that Lisa and I have taught over the years, starting since like 2012, we've given out a longer form that would have a bunch of research questions effectively and answers. So this is sort of drawing it up to get you to go put things in JAGs more than anything else. So we have these groups people are assigned to, and then we went and collected the number of strokes it took them on a high stakes 18-hole round of miniature golf. Hopefully you can tell there's sarcasm dripping through here because high stakes miniature golf sounds awesome. I don't like watching golf on TV. That's like, I guess I haven't fully become a dad yet, but you know.
And that's when you become a grandpa.
Okay. But I probably would watch miniature golf on TV. So, well, probably not. I don't watch a lot of TV. If they had people from Mexico calling the game, yes, the match, probably. We also collected basically a survey that was trying to assess people's enthusiasm for miniature golf. You want to?
Yeah, so the acronym of the survey is yes.
Which is the answer when you say?
If you feel like playing miniature golf, yes.
What should we do? I don't know. You want to play miniature golf?
Yes.
Now I think, oh gosh, what is our 3-year-old going to do with the ball when we take him?
Yeah, I don't want to find out.
So it was a perfectly reliable scale, and it fit a one-factor model, and so it has a mean estimate of 0 and standard deviation of 1. A lot of the things that we asked before in this assignment were to like center the variables and understand how interactions work. I'm not asking any of that. I'm asking you to create a Bayesian linear model that addresses these 3 specific research questions. To what extent does training group experience and enthusiasm? I guess we also collected how long you had experience with golf. So to what extent does training group experience and enthusiasm predict miniature golf performance? To what extent does this effective training group depend on experience with miniature golf? And then to what extent does residual variance differ across the training group? So that last question is not one that you typically think of, but it's me trying to broaden your horizons about assumptions and blah, blah, blah. Had a conversation yesterday about how to address this. And the way I would like to say is I'm sort of being agnostic about the model. Right, there's multiple ways. The main thing I'd like you to do, though, is to make sure that there's one model that you refer to for all your results. Now, how you arrive at that one model is up to you. I'll allow you to decide. Last week we talked a little bit about model comparison. I'm going to go back to those slides today and talk a little bit more about them, about model comparison, comparing models. But you can think of, when you do this type of assignment, there's sort of multiple features depending on what your linear model philosophy might be, or how you learn things, or how you've done things in the past. One is, let me just start by building up by adding a variable at a time to an analysis. And sort of another one is the opposite. Let's throw everything in and start maybe removing things if they don't have an effect, if we can see that. It's a little bit more complicated in Bayesian, though, because what's an effect, right? It's all, I wouldn't say it's subjective, but it's not as cut and dried as looking at a p-value and saying, oh, there's no effect here, I'm going to pull the variable out. Any thoughts or questions about that?
Just a reminder, in golf, higher scores are bad.
Yeah.
So it's backwards from how you might think about it. So fewer strokes means you're doing better.
Yeah, that's also the hard part about this assignment. This assignment is the classic first assignment in a class we used to teach that sort of was kind of the universities worked at before. It could have been the third course that you take in kind of in statistics in grad school, what we call it. At KU, we made it the second course, and this assignment invariably made everybody freak out. But we're not going to freak out in here because it's not about that, right? The nuance of getting into each of those linear, we were trying to basically see, what do you know about betas? What do you know about interactions? How can you form effects? How can you form simple slopes? How do you do these types of deals? We're not going to talk about that. We're just going to address these questions lightly from a Bayesian way. And it takes long enough to put this in code anyway. So, although I'm going to talk about today, actually, so in doing this, just a little bit of a heads up, this set of code should show up first in your analysis. Although you replace your replace this Iowa ID with your 8-digit ID. And the reason for that is that now everybody will get a different data set. Right? We have a common data set, but then you have a different data set that you can go and look at your results for. And actually, I'm okay with you working together on this, because if you have different data sets, then you can have different ways of learning more about showing different types of results. The only thing I'd ask is that when you do the write-up, make it your own words, because as I like tell people, you got to practice writing. Writing's important. I haven't asked people to write enough in my classes, and so I'm just trying to get you to start writing a little bit more. And the way I always tell people when they try to come to work with me for grad school, which is PhD is a writing degree. The problem is I'm not a writer, or I don't know how to train you how to be a writer. So it's a tough call. So anyway, what this is doing is you should, by putting your own 8-digit ID number there, we set the random number seeds for based on your unique combination of digits. So that means each person will have a different random draw of the data. Read in the original data. This sample function effectively goes and does like a bootstrap replication sample, right? So we have 200 observations in the data. We are sampling from it with replacement. And now we're drawing a sample size that's equal to 200 from it. And then to select those observations that we just drew, that's what this code does down here. This takes the original data frame and says, I want only the columns that show up in this part of output. Any questions? Cool. Is this are we good just talking about this a little bit? I feel like I should give you some more description about this. So you can select a single bait, construct a single bait. You can do all this in a single model. The question of what the model looks like comes into, I said, you work your way up to a single model, or do you start with a single model? Again, I'll leave it up to you. I'm not going to critique either way. This is not a class about linear models, so I don't need to get deep into the philosophy of that. And then write a results section. And so this is where I was sort of saying up here in the top, find a paper with a results section. The second one being write a results section. Because eventually, if you're using Bayes to do things, there's a lot of variability in how the results look. Here's what I'm looking for, a model description, but not y equals x, say in words what you're trying to do with the model and why it's there. Why did you choose the priors that you selected? Again, I'm also hands-off on priors. Go ahead, you can choose anything you like. Model and choice for the algorithm specific. Choice and motivation. Why did you choose this? What did you choose? How many number of chains? Why did you choose that? Same thing with iterations. Convergence diagnostic statistics. So do parameters converge? Remember that from last week? There's lots of them. If you run multiple change, Gelman or Rubin seems to show up always, so it's easy to use. Answers to research questions. So basically, now with all this right here sets up the idea that, hey, my model's working, my algorithm's working. Now, once that's established, what are the answers to these questions, and why do you believe that, based on your model data as evidence for it? And if you feel you have other information you feel relevant to provide, go ahead. And that's, I said 500 to 1,000 words. It's not a big amount of writing. I don't think. I don't know what big is. That could be a big amount of writing. If you don't want to do it. I've been there. I know how that feels, right? But just something to practice a little bit of writing with. Okay, the final one we're going to talk about today, derivation of a posterior distribution for beta and sigma squares with the Jeffreys prior. The Jeffreys prior, I actually think I spelled this wrong. It should be Y apostrophe S, I think. Anyway, the Jeffreys prior is a prior that's used in Bayesian. So there's one other issue with priors I didn't mention, and that's that when you choose a certain prior, not all priors are invariant to transformations of parameters. So meaning that if you say, oh, like we're about to do here, it's sigma squared, like the last example in my lecture last time, I said, oh, let's take sigma squared and take a log transformation of it, and then model the log transformation as a log normal distribution. That's not equivalent, so the resulting posterior distribution is not invariant from our choice of not transforming sigma squared. Now, it may be, because remember the impact of the prior can be small, depending on data, depending on signal. This might be a trivial change, right? It may be just slightly different. But if you're thinking about the properties of parameter invariance and variance under linear transformation that we talk about in like maximum likelihood, this could be disconcerting to you, right? So priors that are invariant to transformation, people sometimes want to have for that reason. It's, again, it may not be a big deal, but just to have a heads up is another thing to think about. And the Jeffreys prior is one of these. It effectively is the prior that we basically say 1 over sigma squared, the prior distribution for it's uniform, right? Or so it's every value for sigma squared is equal to like the 1 over sigma squared error. And then the prior for beta is uniform, it's all 1, everything's equally likely as well. If you choose those priors, what you end up seeing is that and I can even tell you what the posterior distribution is. You can go look this up online. It's not a big deal. It's pretty well studied. But the posterior distribution for it essentially follows the limiting distribution under ML, right? So you know what the least squares estimates of beta should be? X transpose X inverse X transpose Y. Right? You know what the least squares estimate of the covariance matrix of beta should be, right? Sigma squared times X transpose X inverse. And then sort of have another distribution for sigma squared that goes with it. We don't really have the least squares, but you can imagine what that would be, effectively what the most likely version of that happens to be. And that now becomes the sampling distribution for each of those. I'm going to show a little bit more about that in lecture today because that's one of the steps of it. How do we get to the posterior distribution? Do a lot of hand waving. But why I pick this is if you follow my notes from today, to do this problem should be a little bit more straightforward where you say, well, that's not there and that's not there. And so if I take these things out and I rework these equations, I'll get to this result. So I'm hoping that will be the case. But if you have issues with this, also come talk to me and we can make it work too. Any thoughts or questions, comments? Very quiet today. Anything happened this week that was fun? No? One snow day for public schools this week. All right, then no questions and comments. The other thing I forgot to do, so I figured out where I screwed up my beautiful example last class. You know, where I'm like, oh, let's fast forward GitHub. Can I re-show you how to fix that? Would that be helpful? I'm sorry that I screwed it up. So I'm starting the day with things I know how to talk about, and then I'm going to go back to the things I don't, slowly. With deriving a posterior being like the crescendo of me going, oh goodness, that's going to take a while. But the issue where I screwed up last time comes from how I didn't just copy or create a brand new folder. I renamed a folder that existed. And when I did that, to update that folder, Git didn't know what to do. So let me show you how to make this work. Let's imagine we have a let's imagine we have a directory that we've cloned into our repository. So I'm just going to do this in command line real quick. All right, so right now here's your GitHub directory. It's grabbing all our stuff. And oops, of course I put it not where I wanted it. Well, I can just do this. So you have the directory somewhere on your disk. You move into it, and we can see all the files that are in there. So this is the brand new fresh copy from the internet. Awesome, right? Maybe you've made changes to it. However you want to do that, what we can then do is change where we create our own branch, remember that thing? So we can do checkout. I think that's let me just go to the steps here. Believe it or not, the steps, had I just followed the steps in my how-to, it would have worked. I followed them this morning to double check right before class. My practice of it. And so here, if we go under the repo, the how-to, fast forward git, and we go to the HTML. We just look at this. Don't want to look at that in the editor. Pardon me. Web browser. There we go. All right. So now we do the checkout and the name of our branch. So we say, okay, I'm going to check out -b, and actually I need git checkout. Whoops. And I'm just going to call this testing. Right? So I'm going to create a new branch called testing. Right? Let's imagine you've made changes to the lectures file. Copy, instead of rename and move the file, what we're going to do is just copy it into a brand new folder. Right? And that's what it said in the idea over here. I created a notes folder right here, so I'm just going to do that. Right, so I created a folder for notes. You can see it's right. Where did it go? There it is. Yeah, right here. Okay, got my notes folder. So now what I can do is copy everything. Let's imagine I just want to copy everything from the lectures folder over. I can do copy. If I do -R on Linux at least, or bash shell, I can copy everything from that folder to notes. Windows is different, but don't ask me that because I'm not good with Windows anymore. So I copied everything. If I show you the notes folder, what you'll see is there's all my notes that I copied over. Now here's the catch. Can I update what happened from the master branch? So what I'm going to do is just quickly go and push another commit to the master branch because I can do that. So I can go commit, testing, fast forward, close, push. So now the master branch has changed. It's like, oh, new lectures come out, right? So now I go back to my command line. It's Friday morning, it's before class. I want to go update my lectures folder with brand new lecture notes. I can go and say git fetch. And so it goes and fetches stuff. It says, hey, look at that. We have a few changes a little bit here. So we can do git rebase origin/master. And then it says, first, for rewinding, head to replay your work on top of it. So it went, grabbed everything that was in the folders that show up in the master, moved it forward, but that folder for notes will still be there with your changes in it. And so now to show that, there's the notes folder right there. Right? Hasn't been touched. So I apologize for not being super awesome with Git yet, but I promise it actually is worth your time eventually to do this. So any questions on Git? Anybody call it JIT? Is it GIF or GIF?
I think technically GIF. I say GIF.
I do too, right? Anybody else? You know what I'm talking about? The image file that ends with GIF? Depends on how you want to sound. I don't know if anyone will ever criticize you for saying GIF, but I've been when I learned it was supposed to be GIF and I tried to say that, people would laugh. Come on. It is. Yeah, and we're, you know, in the language that I grew up learning, J, that's a J. In Italian, you'd want to say GIF, but, you know. Right? Chief? No? Anyway. Okay. So, going back to lecture from last time, I'm going to go to actually, let me stop. Any questions, comments? I feel like class is dragging on here. Just what? Come on, get to the psychometric models is what you're saying, right? Is that it? Next week. Don't, anyway. Let's do this. Let's knit the document. I'm going to go back to the lecture because there were some things I sort of had to speed up through at the end of last week, in particular model comparison, and then we will be able to make this work. Quick question for you while this is compiling. How do you like the notes on RStudio? Is it working or should I go back to slides? Do you think it's all right? Cool. Slide. Who likes slides? It's okay. Traditionalists. Who likes RStudio? Oh, okay. Kind of mix. Fair enough. The problem I had with slides with doing this is I could never, I'm flipping back and forth all the time. And here, okay, I can't highlight enough stuff. It's like I've written a semi-paper to do this, which is also lame. My first class in grad school, probably one of the best classes I've ever taken because it helped me understand psychometrics, was Rod McDonald's test theory. It was before his book was out. But Rod would sit on a table. Was back with the projectors, and he had slides that were that somebody had made from the manuscript, typewritten copy of the book, and he'd just start to underline stuff. I don't remember how much that stunk, right? And so I sort of get that with this. So I haven't quite figured it out yet. So if you like slides, I don't know. It takes me longer. I feel like to compile the slides in this format takes me longer, so I apologize. But I don't know that I can fix it. Seems like there's some people who like RStudio at least, so that's good. Actually, I'll tell you what, in the next couple of weeks, given you know, what's on my plate and whatever, I might just have PowerPoint slides to look at and then go to RStudio too, because the psychometric models, I've gotten slides from previous classes, and I might just repackage those, but then we'll have RStudio examples for how to do it in JAGs. Okay, we talked all about the distributions. We did some analysis. We checked, the first analysis was with conjugate priors. Everything converged nicely. At the end, we did posterior predictive model checks, which really is not a thing for Bayesian linear regression. I didn't actually put it in your homework even. It's for the reason why it's linear regressions, like there's no model fit in it. It's not really a thing. There's one outcome. You're not going to do much with that. But just kind of get you thinking about it. We had the results. We talked about the difference between median and mode and mean for output. That was kind of enlightening a little bit, I hope, at least to me when I was thinking about this. But then I went and started changing things up just a little bit. This was where I changed sigma squared. Well, JAG's model is 1 over sigma squared, the precision for the residual variance, precision. So I took the log of it to model it as a continuous variable. This, by the way, is a hint for homework. Continuous variable goes there. Anybody want to talk about how to make it so it's depends on group variable? Want to talk about it?
Let's do it.
All right. Anybody have an idea? How would we do that? Okay, well, let's take this. Here, right here, I created a variable called gamma 0. This is the intercept of the log variance. Right? So here, down below, what I said with gamma 0 is over here in my notation. which I'm messing around with here. Get to the right spot. Where was that log variance? Oh, Templin. That's the other thing I don't like about RStudio is scaling right now. It changes my code, changes where I'm at. There we go, the model comparison right here. So what I did was I took the log of 1 over sigma squared, and I'm going to say that that value that becomes is just a parameter gamma 0. In homework, to go and model this based on your predictor, basically you take this as your regression part. This is effectively going to be your, how you create in the syntax code. The syntax code. Oh, come on, man. In a regression syntax, remember how we created a weight variable, weight.hat, and that became the mean for the distribution of the outcome? We're going to do an analog for that for the variance. Right? So basically what we're going to do, this is the first parameter of that analog. We would go through, we'd have to put this within the loop because it's possible, it's the people, each person's group may be different depending on your sample, right? We're going to at least have 4 groups, right? And actually, I can just do this real quick here. Why not, right? Okay, tau, what we're going to do is comment this part out here. It just took a screenshot. All right. And we still want tau e to be at the bottom, right? And tau e is 1 over sigma squared. So we have to remember that when we look at this equation right here, that tau e is really this term right in here, this 1 over sigma squared. But when we write out the prediction equation, we're going to have that being a linear model. It's a little bit easier. So at every time we want to switch that linear model back to the log, right now the term on the right hand side is on the log scale, natural log scale. So if we want to convert that back to not the natural log scale, we have to take what's called the inverse link function for it. This is what's called the generalized model. You're probably familiar with them with logistic regression, but you're certainly familiar with them with item response theory if you've taken that before. Right? So in item response theory, you often see the IRT, the item characteristic curve. So the probability of something is equal to, in a logit model, you've got e to something over 1 plus e to something, right? This is log instead of logit. So to go from log back to unlog, you have to take the unlog function, or in this case, e, right? You take the e, Euler's constant. Did I say that right?
Yep.
Go to my math reference here. But it's the inverse function for log, right? So we're able to go, if we take the log of something, we've got the log scale. If we want to get back to the not log scale, we take e raised to that power and it goes back, right? So in my syntax, you'll see I had originally had I put things in the exponent here. We could even just do, we could call it var hat equals, and we can do gamma dot 0 plus, and now here's where we'd have to create a group coefficient for it, right? So in our example here we have 2 group betas, beta.group2 and beta.group3. We would be able to change those. We would have to create those coefficients, those parameters, right here. Gamma.group2 and gamma.group3. We can't use the same parameters. We can't put beta in there because beta is already predicting the mean, and the scale of beta for the mean and the scale of beta for the variance is going to be off, right? So we have to give brand new betas for the mean and for the variance. Right? We could still use, because this log scale runs the real number, the length of the real number line, we could still use priors to do the same. We could still use a denorm prior. We could use this beta mean dot 0, beta tau dot 0, where those are really what we call diffuse or uninformative priors for them. But now, basically, we just have to go and add, I'm going to just copy this. These are the 2 betas for the y part, the mean part of the model, right there in code. We take those to start with because what we see is we take our beta parameter and multiply that by our observed data for it, right? Well, we need both of we need the observed data for our variance as well. So here, we just make sure that we have the right name for our parameters. Right there. So what you'll see now, okay, is that var hat, and actually we're going to have to call it conditional on I because each person may have a different value as we go through the loop, is an intercept plus a gamma parameter, which actually represents the difference between that group's residual variance and the control group's residual variance, or the reference group residual variance. And then the same thing goes with gamma group. Okay, so that goes into var hat. These are all on the log scale, so we have to go and unlog it. So we take var hat I and convert that to the unlog, but now tau e has to have an I coefficient as well because each person may have a different predicted variance. Right? And with that, we would put for each person the tau e into the d-norm function. Right there. Now there's one other catch that goes with all this, that if you typically want to do this type of model, this is, I believe, what we'd call a location scale model, although often you hear the location scale model with the multi-level version of it. I don't know if you've heard of those before. They're pretty cool looking models, basically modeling variance and mean simultaneously. Typically, when you read about them, though, they're not on the scale of precision, they're on the scale of variance. And that's where you can see with this function here, -1 times the log of the variance is equal to this stuff. So if you just multiply both sides by -1, you're back on the scale of the variance. It just changes the sign of each of the parameters if you wanted to report in a more convenient scale. Any questions so far? How's this look? I've never tested this. This is another on-the-fly example. Do you think it's going to work?
It seems good.
Let's see if I can. Now, why I'm saying this, I think it might. Remember, we looked at the plots. It looked like maybe one group had a couple outliers. I can't remember which that is. So we may end up seeing that one group's variance may be significantly different from another one, but I don't know which one that might be. Any questions on this, though, before I get started? This sigma squared tau now is really, this is less important. We could do that with each group, but now we have a lot more things to track. So I'm just going to highlight it and get rid of it. We're just going to think about this in terms of the parameters of the model that are the gammas. The other thing I was going to do is we could actually go and create a difference for the variant, or for the precision between group 1 and group 2 and group 3, because we don't have all those comparisons. Like this. And not only that, this is going to change R squared completely. What is R squared? That's tough, right? Which residual variance are you talking about? There's not one now. There's one per group. I'm just going to leave it open because I don't know that I fully understand the issues in it. There's probably there's lots of ways. I know Lisa and I, mainly Lisa's student, used to look at this, continuing to look into this, and a lot of people have as well. It's not as easy as being like, oh yeah, there's one. Just put it that way. And finally, when we submit this to JAGS, actually I've changed the wrong code there, didn't I? Of course I did. Here. When I submit this part to JAGS, here, I need to make sure that the parameters in this match. So I need to go and take the Bayesian full model parameters, which I created above, and make a good list of those as well. Here's an example of them here. Is this interesting to you at all? Different ways of modeling data? It's a different model. But interestingly, this is the nice thing about this type of setup. It's not unique to Bayes. We could do this with proc NL mix. We could do this with any type of likelihood-based proc MCMC, proc mixed, any other type of likelihood-based system. But you'd have to go and phrase your model similarly in that system to go estimate it. Or proc NL mix, not mixed, but NL mix.
Mixed will do residual variance.
Well, yes, it will, but you don't have to phrase your model this way. You don't have to get, if you're doing NL mix, you have to put all these type of similar syntax together to make it work, is what I'm trying to say. It's
If you use the local option, it looks like what you just did.
mixed, yes. What I'm saying is NL mixed, you make a big long model statement. Mixed, you do not. Yes.
Correct.
Okay.
Yes. M plus 8 also has the capacity to do this.
That's right.
But you have to use Bayes to do it.
Gamma 0, gamma dot group 2 and gamma dot group 3. Okay. Let's see if I can make this work. Jags, of course. You know what I haven't done up to this point? I haven't run everything up to this point. So I've got to run everything into memory. Even though when this is one of the problems I have with the RStudio. When I knit things, it's not putting things in the local environment. I have to go and run things to make things show up in the local environment. And maybe there's an option I'm not seeing or putting in my chunks. But now I think we might be able to do this. I need to change the parameters to save down here as well. There we go. There we goes. Hey! Gamma 0 is not found. Okay, gotta figure that out. Gamma dot 0. Did I spell it incorrectly? Oh yeah, okay. I made a mistake in the spelling of gamma 0. There we go. Now, hopefully it works. There it goes. We're running our model. Okay. Shall we see some results? What do you want to see first? Chain plot? See if it converged? Okay. Oh, that's not it. It was when you use the R2 jags function, the word's trace plot to get a nice chain plot out of it. Yes, hit return to see next plot. There we go. There it is. That's a gamma variable right there. That's group 3. And gamma group 2. Gamma 0. What do you think about that? There's our precision. There's our difference between group 2 and group 3 for variance. There we go. And here's our beta. So it looks like things converged. Should we look at the actual numbers now? The numbers look like this. So this represents what? Tough, right? It is the log precision, but now you interpret it just like you would with dummy-coded regression. That's log residual precision for the reference group, or in this case, group 1. So if you wanted to put this on a better scale, right? If you want to talk about log variance, it'd be -1 times this value, right? Log residual variance, excuse me. And if you wanted to go convert that to the residual variance, you would take E times -1 times that value, and you would get an estimate of that group's residual variance.
Could you ask it to make that for you as part of this process?
Yes, I could. Would you like me to do that?
No, just like asking to do that, like an estimate statement.
Absolutely can do that, yes. So then gamma group 2 is similar to how we reference it in the typical linear model. It's just what we're talking about differs, right? So now this is the difference between group 2 and group 1's log residual precision, right? And she's laughing because try explaining that to some of the best people who are in science, and they'll still go, what?
I honestly don't know of a more intuitive metric. I don't know what the problem is.
I know, it's so amazing. Residual precision. So what this is telling us here, I haven't formed the highest density posterior interval for it, but if we were to take this, which is the credible interval, the 95% credible interval, which giving a look at the, when I looked at those distributions, they looked pretty regular, symmetric, I should say. So it's probably going to be pretty close to the HPD interval. We would want to say, is this the analog? Are these two widely different from each other? Is 0 would be there's no difference in residual variance between these two groups. So 0 doesn't appear in our 95% credible interval. So we'd say, hey, 0 is not likely to be a value that this parameter can take. Like, we have a very good certainty to that. So what's that tell us? These two groups have a different residual variance or different residual precision, really.
So which way does it go then? If this is precision and group 2 is more precise, means they have less
residual variance, that's right. Yeah, and that's where...
Obviously.
Yeah, exactly. How to explain that is harder. Similarly, group 3, that is the difference in residual precision between group 3 and group 1, it does not contain 0 in its 95% credible interval. But so that would lead us to conclude, at least with this level of belief, again, we're talking about beliefs here, posterior distributions, that there's a difference in residual precision between group 3 and group 1. How's that sound? Interesting stuff? So, in light of, and then finally, I guess the last one, comparing group 2 and group 3, it's this parameter. It's the difference. It took group 3 minus group 2 to get this parameter. And you'll note that in this credible interval, 0 is almost just a little bit over, actually right about the 75th percentile where it happens to be. So to me, that's, if we follow a similar guideline of thinking of intervals being about 95% of what we want for the posterior distribution to be covered, 0 is in the middle of that interval. So I think I would conclude that it's possible that group 2 and group 3 have equal values of residual precision. So going back to your original ANOVA assumptions, remember we talked about that the first day, this tells you what?
That homoscedasticity is probably out the window.
That's right. Data are not homoscedastic. My guess is you're not going to see a big difference between these results, though, for this model and the results from the model where we ran the original value. This is the Bayesian full model results here. Oops, I didn't run that model. I'm going to run the model. I think I screwed this up though. No, I can still run this model. Okay. Put this here. I was going to run the model where we didn't do anything to it to compare. So I need to compare the results real quick. And it ran, and here we can see the full model results. You'll note that when let me see if I can find, so here is the results from the location and scale version of the model. Here are the results for the homoscedastic version of the model. And let's take a look at differences. Let's forget about looking at differences of sigma, because that's going to be really hard to compare back and forth. I guess we could look at tau. Here's tau, but we're on the log scale for it. So we know those are going to be different because of the results that we had with the different group values. But let's take a look at the betas. Intercept 170.13, and then their residual standard deviation or posterior standard deviation of 48.156. That changes to 169.802, which is close for the mean, the mean of that posterior distribution. So it's roughly about the same value, but you'll look at our standard deviations bigger now for the intercept. Similarly, the standard deviations are going to be bigger for both of these two effects, group 2 and group 3. Actually, these are smaller for these two effects. Standard deviation is smaller. And the reason for that is exactly what you were talking about, Lisa. In interpreting this, we found that group 2 had a significant, Bayesian, had a,
Yeah,
we believe,
allowed to say significant?
no, that's, the Bayesian police will arrest you and put you in Bayes jail. Bayes will be exhumed from the brave, and I want to say it, you know.
Well, really, there's like a posterior distribution, the probability of them coming to arrest you, right?
And that likelihood goes straight up. Okay, so in this one, we found that this was likely to be different. I'm just going to go cage it in terms of probability or uncertainty. It was likely for group 2 and group 3 to be different, and once you followed the logic that Lisa put together,
Group 2 is more precise, which means they have less variance, which is why the standard deviation is small.
that's what happens. That's right. So now all of a sudden, because of that, we were able to effectively get more certainty on our main part of our story for it. So I think that was kind of interesting. What do you think? Is this a model that's sort of interesting to you? So that's why I put it out to you. It sort of hit me when I was asking about ANOVA like the first day of class. If you were to have this at your disposal when you started, when Fisher, okay, now I'm going to pick on Fisher. When Fisher was around, do you think ANOVA would look different now? All those years that people have spent teaching ANOVA a certain way, worrying about homoscedasticity and so forth, if you said, well, that's just one assumption, but I could just change the assumption and see what happens. That would be very different, I think, right? And it just doesn't have to be Bayes. It can be, like Lisa was saying, proc mixed in SAS, other versions.
Well, it's a modeling perspective. I really like this, by the way. I think this is useful just to think about, because you're told you're making assumptions, right? But really what it is that you've made a choice, and therefore there's an assumption that goes with the choice. So, like if the 3, you know, normality, constant variance, independence. Well, because you picked a normal distribution for your residuals, that's why you're assuming normality. If you need to pick a different distribution, you'd assume that. Now you're assuming constant variance because essentially the model that you started with had no predictors of differences in residual variance. You chose that, and therefore that's the assumption. So rather than saying homoscedasticity is violated, we're saying the new assumption is heteroscedasticity, but it's of this particular form. There still could be other kinds of violations that are not part of our model, but we could make them part of our model and it's no longer a violation. You change the choice, you change the assumption. And then, you know, if you don't want to assume independence, you add another error term and you come to my class on Tuesdays and Thursdays. So then that's your new choice.
So I think that's a good point. The word choice is there, and up until, you know, first certainly modern computing, but also likelihood theory was really implemented in computing. You wouldn't have a lot of choice under this
What you can
paradigm.
do by hand limits the choices that you have. What you can compute by hand in terms of sums of squares initially, and then what you can do with likelihood. Bayes is becoming much more popular in these kinds of location scale models because it's impossible to get like continuous predictors of differences in residual variance.
Yeah.
You can do that, but it's hard with likelihood by itself.
And then also, yeah, so you have to think really hard about your model. But what I'm trying to make you think about is, of all the times you've told that's the assumption, if you go back and sketch, no, that's the choice. I think that's where we're going at with here. It's effectively assumptions are choices now. Whereas before you had the option to do this, and really, I mean, mixed in SAS has been around, what, 20, 30 years almost. NL mixed has been around a long time too. That choice has been around a long time, but I don't think we fully understood that paradigm shift. But I think this indicates something significantly different about what instruction might look like in the future as well. Like, you have to sort of go back and go, oh yeah. Assumption or choice? Assumption or choice, right? So.
Early stats and early psychometrics, like, they did what they could do.
Right. And that, And
they
they
had to simplify things. They had to, make some choices.
and they were concerned about this issue,
Yeah.
but they were able to. Sorry to interrupt. Go ahead.
Oh, no. Yeah, they make some choices just so they could do something. Like, I want to do inference on this. Well, okay, let's assume it's normal so I can make some inferences.
That's good, and it was able to be done. And just like we were talking about with papers, science and science in general, this linear models is still an evolving science as well. I once had a colleague, one of my first colleagues, tell me, "ANOVA hasn't changed in 50 years. We want you to teach that." And I think that colleague, if he would probably remember it these days, he'd probably go, I totally didn't understand now, because I think I've seen him change as well. But it's an interesting world. So I hope that I'm dwelling on this, but that's sort of it. So the question I have for you though is, which model do you believe more? And how would we tell? How about we look at model comparison statistics? The deviance information criterion is the one that we use a lot in Bayes. It's not perfect. It doesn't have a metric that says how much smaller one model has to be for the other. The deviance information criterion, if you want to know how you compute it, at the bottom of the lecture, we talk about this here. This term right here, really what the DIC is, we want this D function evaluated at our average value of our parameters across the chain. What is this function? This is the likelihood of the data given the parameters. That's your model right there, right? And so you've got -2 times the model likelihood. In building all this, you evaluate it based on kind of the average that happens at every step, across every step of the chain. This is the deviance. At every step of the chain, you can calculate it. If you're using the R to JAGS package, it loads a module called the DIC module into JAGS, where it automatically tracks this for you. And you can see it wiggle throughout the chain, right? That's effectively data likelihood given the parameters at that step of the chain. We're basically taking a function of the average of that and comparing it to the average for the mean of the chain values, and then penalizing it by the effective number of parameters. That's what they call it. There are multiple ways of calculating the effective number of parameters. There's some argument as to whether one's better than the other. It's not resolved, but this is a fairly close result for it, for what you see. But if we want to compare that, what this allows us to do then is look at, when we're done with our analysis, we can then look at the value of DIC that comes out when it's loaded. And so the smaller one turns out to be better, lower DIC is better. Here, a model that we added, we actually had 2 more parameters in our model, right here, and our DIC was 184.0. This was the location scale model that we just created. If we compare that with the model without the location scale, the DIC was 248.1, much higher. And so if we were to go back to these results, what we would say between these 2 models is that we would prefer the one that had the location scale.
Would it be fair to say that is the choice that closer meet the assumptions of that choice the one that will give you the best model fit? That
is typically what we like to think of it as. And I say it hesitatingly because I don't know all of the cases where I might be wrong, but I think that's how I look at it. If the model fits the data better, it's more effective at describing what's happening in data. The DIC will be lower because of it. Yeah.
2 questions,
Mm-hmm.
one quick, one longer. So you're looking at the point estimate of the deviance, some sort of central tendency.
That's right.
Would it make sense to look at the intervals and talk about whether they overlap the same way you're doing
You can.
credibility?
You can, but the deviance itself is not weighted by, so the deviance, what you would get from a plot that we would show here. I hesitate to do this, but I'm going to pull up a plot of the deviance. It's just going to take a couple minutes. Trace plot does not work well with what I'm doing here. Let's see if I can find it. There's deviance. All right, so here's our model deviance. This is, again, the data likelihood where we plug in that chain or that iteration value of the parameters. This is a raw statistic that's not weighted by how many parameters we have. And that's okay, people still use it. That doesn't make it bad. There are ways that we can trick this into coming up with something called a Bayesian P-Value. People say that, but effectively, if we look at the deviance for this is a posterior distribution of deviance now, right? We could look at the posterior distribution for the deviance of the other model as well, and effectively, if we were to go and just randomly sample draws from this, although it's a little bit harder than that because there may be a covariance between deviances, we could try to figure out where the overlap might be, like you're saying, and that does happen in some cases.
That's not a thing normally.
Not normally a thing, no. And the reason for that is like AIC and BIC, there's a penalty function based on how complex the model is that's not factored into deviance.
And that's my second question, is what is that penalty function? In your notation, I don't think it's defined what the things stand for.
2PD
You've got
is a...
D hat and then minus D theta hat.
Yes. It's something where we're trying to create what the effective number of parameters are. And what that means are parameters that are doing things to our likelihood that are changing. And so why I say that is you can put a bunch of different priors on, or you can think of the hyperpriors as having parameters, right? So it's not just like, here's beta. Well, beta has 2 parameters because you said it had a mean and the variance, right? So we have to come up with some type of version of effective number of parameters. It's hard to think about what that might look like. Is that weird? So effective number of parameters essentially is trying to say, when you put your model together with your priors, because the priors will have parameters too, it's sort of trying to weight how effective those parameters are, those prior parameters are at building your model. And you think about what we could have done with this. We could have said, oh, you know, we've got a bunch of betas. The prior mean for it, I'm just going to take the mean of all the betas. I could build an empirical prior for it, or something like that. There's ways that we can play around with this. So the number, that's why we can't say that directly the number of parameters. We sort of come up with an effective number of parameters for it. It comes from the difference between the average deviance across the chain. The average deviance across the entire chain, right? So the average of this plot right here, minus the deviance that's calculated, model data likelihood, calculated by plugging in the average of our parameters, the EAP estimates at the end of the chain, right? So what does that mean? How far is the chain-to-chain average, or the iteration average, from sort of the central point in general? I don't understand the theory behind it. There are a number of papers on the topic, starting with people who developed bugs first, Spiegelhalter. There's another version of the PD that comes from, I think, Plummer, and I think Gelman's also looked at it as well. I don't have the reference list, but
Is it kind of like wiggliness?
it's like model complexity. It's like an estimate of model complexity, because you can get really crazy with things that don't touch data in Bayes. So it's not easy to describe. I don't know that I fully appreciate it either. But let's just compare that real quick. For the model that's not location scale, 24.2 is the value. That's effective number of parameters. Well, how many parameters would we look at this like if we were doing a regular, like in ML, or how many parameters we have? Well, we have 1, 2, 3, 4, 5, 6 betas we think about in ML. Well, we have 24 parameters. What are you talking about? Well, we also have a tau in Bayes. That's 7. And depending on how we parameterize these, some of them have, if we think of their mean, even though we fix the value of it, they sort of have a distribution that could have a mean, could have a variance, could have covariance between them. So that's where we get 24 from that. Whereas for our model that we think fit better, the location scale, it's actually 12.5.
What?
Yeah. So
They have more. How can it have less?
because they're effective. It says.
What is there?
More is less. Less is more.
Well, you know, they're on the log scale. No, I'm just kidding.
No.
No, it's because of the, like, when you put that in, you get a smaller difference between the iteration to iteration average of deviance and the final value of deviance that or the final value, the deviance that you get when you plug in your final parameters.
That's what I was trying to say with looping.
Yeah.
It's like if the average is right on top of, if each iteration is right on top of the average, like, versus like it just goes all over the place.
That's right. It's tough, huh? Is this good or no? Too much?
Yeah, so I guess it's like, if you have a lot of parameters and they suck.
Yeah, that's it. That's exactly it.
Right? Then it's really high. But here we've got more parameters, but actually, how they're working all together is doing a really good job.
That's exactly right. Yeah, like, and if we would have had one of these that, you know, if only one group's gamma would have been further away from zero than both of them, we probably, you know, we would see that. We'd just be a higher number. So.
It's like efficiency rather than.
Yeah. That's like effective, meaning like that was really effective. Like, you know, penicillin's really effective.
I think an effective.
Well, actually, I shouldn't say that.
Like in cluster samples.
Right. Yeah.
That makes me think of, but that's not.
And that's actually this thing over here. This is based on how clustered or how much autocorrelation is in your chain. You can talk about how many effective draws that you have from the posterior. Okay, other thoughts or questions? Okay, we were going to do algorithms. We're going to get those next. And, we're going to take a 10-minute break, come back around 10 till 11, and we'll load up math.
So if we were going to go and rebase, would we have this new syntax?
Not yet. Do you want me to push it?
Yeah.
Okay. I'll do that. All right. Actually, I need to copy. I'll copy and paste the old one. I'll try to do that in the middle of the break. So, thanks, everyone.